Okay, guys. Let's look at this last page on the diene. First off, any questions about dienes? Diels-Alder, 1,2,1,4 reactions. Questions about dienes? Question, Valerie? On this page or another page?
Yes, for the second one.
This one right here, which cation are we going to form? You got to react. You got two different double bonds. You got to see which one's going to give the best cation. If this double bond reacts, we would put plus here, correct? Where are you going to put plus? Right or left? Left. H plus here, we get boom, 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 boom. New H there, plus there. We've been doing that for 6 weeks now. And then we would have resonance. Windshield wiper over. Resonance would give boom, 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 boom. Here, plus here. This is one cation. The cation has secondary.
Tertiary. You forgot a methyl.
Forgot a methyl, yes. There's a methyl here. That's tertiary, and then this is secondary. One cation has characteristics of both. The hybrid would have characteristics of both of these. Then we could try the other double bond. H plus, we would pull away here and put cation. New H here. Oh, 1, 2. Boom. Boom. One there. New cation here. Cation would be there because you're resonance stabilized. We would never put cation here. We want to do resonance, but then when we do resonance, we get cation. It looks like this. This is one cation. This cation has characteristics of secondary and primary. Which cation is better, secondary primary cation or tertiary secondary? This is the double bond you're going to react. From now on, forget about this. I could either add there or there. If it was cold temperature, it would add here, 1, 2. With heat, we get the most stable product. Most stable product would be hold on, we're missing methyl here too, yeah. Here? Methyl is also missing there. Most stable product would be this. I'm adding here. To give a tri-substituted alkene, that's only di-substituted. Cold temperature would add here, warm temperature I would add here. Did that answer? Anybody taken an aspirin recently? Aspirins inhibit cyclooxygenase enzyme. What does this enzyme do? It converts arachidonic acid, which is in your body, to this species here. It's called an endoperoxidase. Or endoperoxide. It's got two oxygens bonded together here. First reaction though, this is sort of like a cycloaddition. It's not exactly a Diels-Alder, but it's somewhat related. Involving oxygen. It's assisted by an enzyme called Cyclooxygenase. Oxygen can be drawn with the double bonds, like this. Two oxygens end up adding to here and here. This can be shown in a number of ways, but we can show these electrons breaking away from that carbon, attacking the oxygen. These electrons adding here, and then these have to break away. These break away. This needs electrons, so this can come down and make a bond right there. It's a concerted transition state, pericyclic reaction. This electron movement here gives this. You've got this CH2 bridge between here. Right here we're making a single bond. It's not exactly a Diels-Alder, but it's similar. This takes place in your body. Aspirin inhibits this enzyme, keeps this from occurring as much. This is in the synthesis of prostaglandins. This goes on to prostaglandins. They have different functions in your body. This prostaglandin increases blood aggregation. And so we know that aspirin is a blood thinner. This keeps this from forming by blocking that over there. And thus you don't get as much blood aggregation. Aspirin also inhibits inflammation. That's because this prostaglandin here produces inflammation in your body. If you can inhibit the production of this way up there, then you will have less inflammation in your body. So this is biochemistry, this is drug design, and this is somewhat similar to a Diels-Alder with oxygen. So just an application of some kind of cycloaddition type chemistry. But we need to move on to mass spec. The first thing we can talk about with mass spec is IR. Look at this page here. There's two alcohols at the top, and there's two IRs. Can you assign structure to spectrum? Which alcohol goes with which IR? Both IRs show an OH. Both IRs show saturated CH. It's nearly impossible to match them up. IR has limitations. It shows functional groups, but it tells you really nothing about the backbone. You know, it didn't tell you if you've got 5 carbons or 10. It just tells you have saturated CH, sp3CH, and an OH. Fingerprint. Of course, the fingerprints are different, but unless you have a standard to match it up, you can't tell which is which. Just like if you find fingerprints on a doorknob, it could be anybody. But unless you have a standard on file to match it up. So, IR has limitations. Now, if you look at the two compounds, they have different masses. Because this one has 1 extra carbon, and thus extra H's. The mass of this is 14 higher, CH2. So if we had a technique that could determine masses, then these could easily be determined. And indeed, that's what mass spec can do. This shows mass spec, but let's flip over one more page. This shows the mass spec of each alcohol. Along the x-axis we have essentially molecular weight. Okay, we'll see it's called a mass to charge ratio, but it's essentially molecular weight. As long as the charge is +1, and it usually is for us. The top alcohol has a molecular weight of 60. The bottom alcohol has a molecular weight of 74. Right here we see a mass of 60. We'll learn how to read these. And the one below we see a mass of, it's a small peak, but right there it's 74. And right there we can tell which is which. Okay. First question we need to answer is, how do we get signals for mass? Why do we get a signal? This is the signal here. The signal is relative. That is, this compared to this, it's much smaller compared to this signal. This is a giant signal. How do we get signals for different mass? Well, let's look at the previous page, and let's look at what's going on when we do mass spec. Basically, here's a summary of how we get a signal. There's some physics law out there. I think it's Newton's second law. Force equals mass times acceleration. Is that it?
No.
I haven't had physics in a long time. Force, mass. There's mass right there. The force here is going to be a magnetic force, magnetic field. And the particle or the compound is going to have a positive charge. And if you put a positive charge in a magnetic field, there's going to be a force acted upon it. And it can be deflected or accelerated in one direction. But there's a mass term in there. And the degree of deflection in the magnetic field is dependent on the mass. And which is going to be deflected more, a heavier particle or a lighter particle? Lighter particle will be deflected more, assuming the charge is the same. Because charge could vary. And that's basically what's going on here. The first thing we do is we have to give the compound a charge. Once we give it a charge, then we shoot it towards the magnetic field, and as it enters this magnetic field, it's deflected because the field deflects the charge. But the degree of deflection is based on the mass. Lighter particles are going to be deflected more. But the degree of deflection can be quantified. And we can plot that. And that's what I showed you before. That was a plot of masses based on deflection. Okay, let's restate that going through step by step. You have a molecule, like one of those alcohols. The first thing you got to do is you got to make it an ion, a positively charged species, a cation. How can we make a molecule an ion? A cation. We get it to lose an electron. Okay? Here we go. Here's a molecule right here, Joy. If I'm going to make her positively charged, I got to get her to lose an electron. How can I get her to lose an electron? Well, there's a number of ways now to do that. But one way is I can shoot electrons at you. And if I shoot electrons at you, those electrons could kick one of your electrons out. I'm going to shoot an electron beam at you. Here comes the electron beam. It hits the molecule. The beam just keeps going. This is the electron beam. But it causes an electron to be ejected. It shoots out. And then you're left as the original molecule without an electron. You're going to have a positive charge now because you lost an electron. But you're also going to be a radical. Because originally all your electrons are paired. If you lose one, then there's going to be one that's not paired. Loss of an electron forms a radical cation. Positive charge, but it's also radical. That's the original species it's formed. This is called electron impact when we use an electron beam. That's one of the most common ionization techniques. There's newer methods available. In 2001 or 2, somebody won a Nobel Prize for a newer ionization method. This is the old standard. Now, once this becomes a cation, we can send it through the magnetic field, and as it's going through the magnetic field, it will be deflected because it's charged. But the degree of deflectance will be based on its mass. The lighter the mass, the more it's going to be deflected. So right there, we can go back and look at the previous page. And say, hey, let's put this molecule into the mass spectrum. Let's shoot it with an electron beam, electron impact. Let's get it to eject an electron. When it loses an electron, what does it become? A radical cation. Once it becomes a radical cation, we can send it to the magnetic field, and it will be deflected. Once it's deflected, it can hit a detector, and we can get a signal. But right here, where it says 60, this is the signal for that radical cation being deflected. Now, how do we get all these other signals? Why did we get something at 31? Let's go back to the previous page. By the way, this species, the radical cation, is also called your molecular ion. It's the full molecule, but it's an ion. But the molecular ion can also fragment. It can break apart into many different smaller ions. Importantly, when the radical cation fragments, it forms radicals and cations. Only the cleaved cations will be observed, because only these will be deflected to the magnetic field, and only these will give a signal. We'll never observe the radicals. But these will be cleavage peaks. They'll have a lower mass than the original mass. Sometimes these are called daughter ions. And if we look at the next page again, we can see some examples of daughter ions. This is molecular ion. This would be called M+. It's actually a radical cation, but often it's just called M+. This peak is at 59. That means the mass is, we can say, M-1. That makes sense. It's 59. It's 60 minus 1. 1 is typically a hydrogen, and I've proposed that this be the structure of this fragment, where it's just lost an H. This is a cation because only cations show up. This signal here is 31. So first off, we can call it M minus, what do you have to lose to get to 31 from 6? M minus 29. We can call that M minus 29. That means the original molecular ion has lost 29. 29, we'll learn, is usually an ethyl group. 2 carbons and 5 H's. 29. If this loses an ethyl, we could show something like this cation. So back over here, original radical cation can give a signal, but it can fragment, and you can also get signals from daughter ions. Only cations. Radicals are not seen if they're neutral. Only positively charged species will be pulled towards the magnet and deflected. This shows an overall schematic of the instrument. We insert the sample. Usually it's done as a solution. IR, you don't make a solution, you put the compound directly on the IR. You dissolve it in a solvent. You inject it, usually with a syringe. This is all under vacuum. It's pulling the molecules this way. You encounter the electron beam, which is where you do the ionization, the electron impact. Ions are formed. They're pulled towards the magnet. And when they encounter the magnetic field, they're deflected. The degree of the reflectance correlates to the mass. And we can plot the degree of deflectance, basically. Basically, something hits a detector. There's many ways to detect the ions. For example, the ions can cause a current to be produced. So that's how we plot the different masses. The intact molecule may make it all the way through to the detector. If so, you would get a signal for the intact molecule of M+, which is the original molecular weight. Or the intact molecule may fragment as it's going to, and you may get the daughter ions that are deflected, and thus signals for the daughter ions. There's an example below of a different compound. When you take this ether, put it in the mass spec. First off, the molecular weight is 122 if you add it up. You inject it, it undergoes ionization by electron impact. What does it become? Molecular ion, which is a radical cation. The mass is still 122. When you lose an electron, your mass doesn't change. Not as a whole number. Electron has a very small mass. Doesn't change as the whole number mass. This could survive and hit the detector and give you a signal at 122. Or it could fragment. We'll learn common fragmentation patterns. One common fragmentation pattern for an ether is to cleave next to the oxygen. Between the alpha and beta carbon. If it cleaved here, we could propose this cation and this radical. Remember, what do you get when a radical cation cleaves? Cation plus a radical. When this radical cation cleaves, you get a cation plus a radical. Which one of these gives you a signal? Only the cations give a signal. You'll never see this signal. But you may also get a signal at 107, which is what? This minus 15? In terms of terminology, you can say M minus 15 or M plus minus 15. This is lost to CH3, which is 15. 12 and 3 is 15. So ultimately, you may get a signal at both places. And there may be other signals. Just like in IR, we don't identify every single peak in the IR. In mass spec, we won't identify every single peak. Any questions about the general idea of mass spec? We'll look at examples of different types of compounds. Any idea about the chemistry or physics or anything here that's going on? Ionize the molecule, send it towards a magnetic field, it'll deflect. The deflectance correlates with the mass, and we can plot that. Now, what are we doing? Getting mass. Isn't that very powerful? I mean, IR doesn't give you mass. It only gives you functional groups. So this is a complementary type of, I would say, spectroscopy. But one point about that. Spectroscopy implies we're using light spectrum. Spectroscopy. We're not using light here. So it's not correct to call it mass spectroscopy. Instead, it's called mass spectrometry, because we're applying a spectrum. But it's actually, we're not using spectra, light spectrum. One comment over here. Why is the molecular ion so small for 74? Well, sometimes once the molecular ion is formed, it's fairly unstable and it will immediately fragment. If it immediately fragments, hardly any of the original molecule will hit the detector. So it seems like this was pretty unstable and it immediately fragmented to form. What was the most favorable fragment that formed? It would be 45 because it's the most intense signal, meaning a lot of that fragment hit the detector. The most intense signal is called the base peak. That's the peak that registers as 100%. And everything else is relative intensity to that.
Understand. So the highest tick on the mass percentage on the bottom, that is the molecular ion. It's like 74 in this case.
Molecular ion right there.
Is it always the highest registered peak?
Hold on, that's 73.
Right there.
Yeah, 74.
I was thinking of a 74. That's not even 74, is it? That's 73. Yeah, the molecular ion is not even showing up. Sorry, that's not even the molecular ion. 74 is right here. There's nothing. There's no molecular ion there. What does that mean? Well, first off, maybe it's not the right compound. If it is the right compound, that means that the molecular ion was so unstable that as soon as it became an ion, it immediately fragmented and none of it ever reached the detector as the intact molecular ion. And that can happen. For us, it would be kind of rare, and this is an example. But the molecular ion may not survive to hit the detector. It may immediately fragment. Question over here.
Yes, you said that the most intense peak is the one that hits the magnet first? Or
No, the most intense peak is called the base peak. The most intense peak is, I didn't say anything about hitting the magnet first. Did I say something about hitting the magnet first?
no, I was trying to figure out what you said.
No. Tallest peak is called the base peak. What we can take from that is this is apparently the most favorable cleavage peak. There's more of it.
That's the most fragment that hit the detector.
Yes, this is the most prevalent fragment that hit the detector. That's why it registers as the most intense. Base peak. Molecular ion apparently didn't survive and hit the detector. The question was, is the peak to the right always a molecular ion?
The furthest peak to the right.
Well, not always, because the furthest peak to the right is 73. Molecular ion should be 74.
Will we know the molecular ion that we're testing before we read this?
Well, you know what you think you should have. If you got a compound with a molecular weight of 200 and you shoot it into the mass spec, you're looking for a molecular ion of 200. If you see it, you say, yes, there it is. If you don't see it, what do you say? It either is not the right compound, or the molecular ion didn't survive to hit the detector. So not having a molecular ion leaves you to have to speculate, or, okay? Of course, what if it gives you a peak at 200? Does that mean you have the compound you think you have? Not necessarily, because there's probably lots of compounds that have a molecular weight of 200. You have to look at cleavage. Do you have the predictable cleavage? Does your IR match? You're building a case, okay? You don't just have one piece of evidence. You have many pieces of evidence. Do they all support what you think you have? Okay, let's look at example compounds. As with everything, as we go through this, we will see more and more what mass spec is, and other questions will come up. Okay, let's start with just simple alkanes. This is a compound 1, 2, 3, 4, 5. Hexane. Hexane has a molecular weight of 86. If we get it to ionize for a molecular ion, if the molecular ion hits the detector, it should give a signal at 86. Here we go. 5. 1, 2, 3, 4, 5, 6. 86. M plus equals 86. We have a molecular ion at 86. This is consistent with hexane, yes? Of course, it's also consistent with 3-methylpentane. Here's 86. Now, what is all these other peaks that are not 86? Fragments is where the molecular ion fragmented. Where's the base peak? What's the value for the base peak? We've got lots of tall ones, but we have this peak at 50, 1, 2, 3, 5, 6, 57? Which is M minus what? Knowing what you lost is important because you can see what you lost. Yes, it's 57, but we can also say M minus 29. And what's a 29 typically? I already told you one time. 29 is typically an ethyl. CH2, CH3. If we lose that, that's 29. 2 carbons is 24. 5 H's is 5, 29. What if you just lose a methyl? What is that? M minus 15, M minus 29. What if you lose a propyl? $45. Okay, so there's some basic things where you can lose. Lose 15, lose 29. Okay. M minus 29, it looks like this lost an ethyl. We can have 1, 2, 3, 4, 5 here. Sometimes I show the radical first, cation, I don't know which goes first. Either way. Radical cation, it can cleave. Basically, bonds get cleaved. Now I show this sort of generically. This is sort of like, sometimes you guys do charges in Gen Chem where you just put the charge on the top right corner. I hate that. But it's kind of like that. You know, this is not meaning that that's plus. Somewhere there's an atom that's missing an electron. Sometimes you can put this with what, like a, no, that doesn't look right. Sometimes with a bracket up there. I'll never do it. I don't know if it's, And that doesn't look right either. Okay, this thing can cleave. How do we lose 29? How do we lose an ethyl? It could cleave like right here. We're not going to look at mechanism for this cleavage. It's just cutting the molecule in half to give, if we cleave there, we would get that plus that. That's 6 carbons. When you cleave, how many carbons total are we going to have? 6, not 7. Okay? This is no longer bonded to that. Now, when the molecular ion cleaves, what do you get? A radical and a cation. Which one is the cation if we have a peak at 57? This is 29, this is 57. Which one is the cation? That's the cation. What is this? Radical. Radical cation cleaves to give a radical and a cation. 57 shows up right here. 29 does not show up. It's not charged. Apparently this is a major cleavage pattern because that's a tall peak for 57. How do we get a peak at 29? There is a peak there. Instead of cleaving this way, it cleaved this way to give an ethyl plus a butyl. And maybe instead of that being the radical and this being the cation, maybe this was the cation and this was the radical. If it cleaved this way, this would not show up, this would, and you would get a peak where? 29. There's other ways to cleave. I cleave sort of right in between and got this cation. Which is a better way to cleave? Not based up there, but based here. Look what we have. Actually, I should put the plus. When we cleave, we can then put the plus in a precise place. It's going to be here. One atom becomes radical, one becomes plus. We're not going to go mechanism, but we can do that. Over here, plus and radical. Sorry, I should have said this right here. Which cation is better? By the way, is this primary, secondary, tertiary? Primary. What is this? Primary. Is either one better? They're pretty much the same. We look up here, we see that clearly forming the 57 was better than forming the 29 because it was taller. But it's not easy to rationalize why. Primary and primary is just as good or just as bad. Question?
I thought you said that the radical didn't show up. So wouldn't the 29 be the radical?
No, it's a cation.
What about on the other side though?
No, that doesn't show up. It's not a cation.
Then why is there a 29 and a 57 that show up on?
The 29 came from this pathway to give 29.
So it can cleave.
The 57 came from this pathway to give 57.
Okay.
Two different pathways.
And it's showing both of them?
Yes.
Okay. But you can tell that the 57 is better because it's the bigger fragment.
Correct.
Okay.
Let's look at the one below. The one below, you don't have a lot of tall peaks. You only have one kind of single tall peak. It looks like the cleavage was more preferred to give this. First off, this is the molecule. It's 114. Now, since there's no 114, we have to assume there's nothing there. So there's no molecular ion. No molecular ion. If this thing formed a radical cation, we might expect 114, it's not there. If this thing cleaves, we can have carbon-carbon bond cleavage anywhere. You can even have carbon-CH or CH cleavage. I've already given you the structure. This thing cleaved right here. And apparently cation here plus what? What else would be? Plus this radical. Apparently that's where it cleaved. This has a mass. It's actually mass to charge, but for us it's the mass equals, what is this? 50, 57? Was the one above also 57?
Yes.
57. That means it's M minus what? It's actually M minus 57, isn't it? Because 114 minus 57 is 57. Why did it preferentially cleave here to give this cation?
More electrons.
What's so good about that cation? Tertiary cation form. When the original molecular ion cleaves, it will typically cleave to give favorable cations. Your more favorable cations are going to be formed. And this is an example where you could cleave to get a favorable cation, and that's why the base peak is sort of so predominant compared to the others. In the spectrum above, no matter where you cleaved, it was going to be primary. And so it sort of cleaved all over the place. That's why you got so many tall peaks. The one below, cleave here, tertiary, boom. Why did the molecular ion not survive? Probably because it wanted to cleave so readily and give this tertiary cation. It was so eager to cleave that it just didn't last long enough to hit the detector. Now there's other peaks. Here's a 29. What is the structure for this here? I mean, it's probably this cation, just an ethyl cation. Where maybe it cleaved right here and gave this radical and an ethyl cation. But that's not a favorable cleavage, because that's a primary cation. Tertiary cation is much better. On this page, we see examples of alkyl bromides and alkyl chlorides. These two halogens have major isotopes. An isotope has a different mass. And we can see different masses on the mass spectrum. If you look at this compound, 1-bromopropane. You can have molecules where Br is 79, but you can also have molecules where Br is 81. Two different major isotopes for bromine. For these two isotopes, the natural abundance is about 1-to-1, or 50-50. Now when it's 79, this is 122. When this is 81, this is 124. We see right here we have 122 and 124. So here's your molecular ion for each of these compounds. Often this is called M and M plus 2. And And you see they're about equal intensity because it's about a 50-50 ratio of these two. You know your salt shaker at home with sodium chloride? Some of the chlorine in that salt shaker has a mass of 35. Some of the chlorine in that salt shaker has a mass of 37. We'll look at it down here. How did this thing cleave? Well, the base peak is, what's the value here? 20, 35, 43? Is that 43?
It is.
Yes. It looks like it cleaved, if we're going to get 43, that's a standard propyl. Cleave here to give this plus what? Bromine what? Radical. Cation plus a radical. This shows up, gives a peak at 43, this never shows up. So it looks like that was the cleavage that took place. Of course, there's some others here. This pattern here, where it's kind of 1-to-1, M and N plus 2, this is called your isotope pattern. Bromine isotope pattern is an M and N plus 2 of about equal intensity, because the two isotopes are about 1-to-1. We can tell that this signal does not have bromine. First off, bromine is 79 and it would never be 43. Any signal that contains bromine is going to be two peaks, sort of the same height. You see these right here? That looks like a bromine isotope pattern, where they're the same height, difference of 2. Where this is what? What is this signal? 105, 107, 109? That's loss of what? 22 to 7 is 15? 24 to 109, 15? This is what? M minus 15? That's where it lost out here. That stayed charged. Because it has bromine, it's 107, 109, but it's M minus 15. So you can tell that that's isotope pattern. Chlorine also has isotopes 35 and 37. For chlorine, the natural abundance is 3-to-1. Not 1-to-1, but 3-to-1. This compound here, when that's 35, that adds up to 78. When it's 37, it adds up to 80. Right here, we see 78 and 80. But it's in a 3-to-1 ratio, which is a standard chlorine isotope pattern. This looks like an isotope pattern here with loss of 78 to 63. That's M minus 15. For both of these, that loses 15 here, this loses 15 here. So it looked like it cleaved here to give that plus what?
CH3.
CH3 radical. This doesn't show up. That shows up here. You got 35 and 37. That didn't appear to be a major cleavage pattern though. This was more predominant. To get this, we cleaved here. To give this plus Cl radical. That shows up, what's that, 43? And the chlorine radical doesn't show up. Why was it better to form this cation than that cation? That's actually not a good question. Let's don't look at that because that's counterintuitive. It doesn't make good sense. Let's look at the next one. By the way, fluorine and iodine, the other two major halogens, don't have major isotopes. Fluorine is all 19. And iodine is all, what, 120? What's iodine, Mark? 126? I have to get my periodic table out. It's somewhere around 126. I don't know, 127. Let's look at this compound. Let's finish up here. This is an ether. From here on out, we're going to get more and more predictable cleavages. And what we need to look at is something called alpha cleavage. And really from here on out, we're going to look for resonance stabilized carbocations. Those are going to be preferred. Please look at cleavages of different functional groups and look through this packet. We have ethers, amines, aromatics, carbonyl compounds. And look for something called alpha cleavage. Functional groups usually cleave in a very predictable manner. In lab, this last week we made a ketone. How do ketones typically cleave? That's one thing we need to ask. For lab, we no longer have Reaxis database. You're asked to look up the boiling point there. Instead, we have to use SciFinder. I'll have to send you some instructions on how to use SciFinder. In lab this week, we'll do mass specs, the first sort of half of lab for each group. And then after that, we'll have lab lecture. Then the group report will be due next week when you come to lab. Okay, guys. See you soon.